The Mitsubishi A6M5 was the fastest variant of the primary Japanese fighter aircraft during World War II. It carried heavy, wing-mounted 20mm cannons, reached a top speed of 331 miles per hour, and sustained a massive operational range of nearly 1,200 miles. Yet, fully loaded, it weighed just 6,797 pounds, less than half the takeoff weight of its American rival, the F4U4 Corsair. To achieve this disparity, designers stripped bulk everywhere. The aluminum skin was milled to 0.02 inches, roughly 5 stacked sheets of paper. By obsessively optimizing for mass reduction, Japanese engineers achieved heavy fighter performance using a relatively low-output engine. To understand the mechanical trade-offs of this design, we have to look inside the A6M5 and rebuild it system by system. Every competitive advantage the airframe held over the Pacific, and every fatal vulnerability it suffered, stems directly from this foundational calculus of weight at all costs. This photograph captures the hollow fuselages of Japanese wartime aircraft moving down the factory line. To mass produce an aircraft this light, the structure itself required specialized metallurgy. The majority of the Zero's internal frame and outer skin was forged from a proprietary zinc-aluminum alloy developed by Sumitomo Metals, called extra super duralumin. This alloy yielded 30 to 40% greater strength than the standard duralumin utilized in American aircraft at the time. This high tensile strength allowed the ultra-thin outer skin to safely carry part of the structural load alongside the internal frame. But that strength came with a severe chemical drawback. Extra super duralumin had exceptionally poor corrosion resistance. Engineers explicitly accepted this flaw, calculating that a frontline fighter's combat lifespan would rarely exceed 4 to 5 years in the field. They applied a similar efficiency to the internal geometry. The two primary main wing spars were built as single, unbroken units running straight through the center fuselage. Passing the spars continuously through the body completely eliminated the need for heavy steel attachment fittings where the wing meets the fuselage, instantly slashing roughly 100 pounds of dead weight from the airframe. Powering this lightweight frame was the Nakajima Sakai 21, a 14-cylinder, air-cooled radial engine displacing 27.9 liters. The engine utilized a downdraft carburetor, requiring the main air intake to move from the bottom to the top, channeling air straight down into the cylinders. To maintain power in thinner air, a 2-speed centrifugal supercharger used a spinning impeller driven by the engine shaft to heavily compress incoming air. This chart tracks horsepower against altitude. Thanks to the supercharger, it maintained 980 horsepower, even at 19,685 feet. But the defining feature of the A6M5's engine setup was its exhaust system. Designers mounted 11 individual exhaust stacks directly to the cylinder heads. Arranged with 6 pipes on the right side of the cowling and 5 on the left, these short stacks were specifically angled to expel high-speed, hot gases directly backward. This rapid rearward expulsion generated a measurable amount of supplementary forward thrust. Combined with the Model 52's shortened 36-foot wingspan, this exhaust configuration pushed the aircraft to its maximum speed of 331 miles per hour. Inside the cockpit, the primary flight controls were entirely mechanical. The pilot manipulated the control surfaces through a direct physical network of cables and pushrods with zero hydraulic power assist. Designer Jiro Horikoshi deliberately specified exceptionally thin control cables for this network. When subjected to high aerodynamic forces, these cables would physically stretch under heavy tension loads. This elasticity gave the pilot precise tactile feedback and naturally prevented them from over-controlling the airframe and overstressing the wings during a high-speed dive. However, the Zero possessed a massive aerodynamic bottleneck at the trailing edge of the wing. To further shave weight, the ailerons were built with a duralumin frame but covered in doped fabric rather than metal. Because of their length and fabric covering, dynamic air pressure at speeds exceeding 200 knots caused these control surfaces to become prohibitively stiff. The physical force required to move the stick left or right became nearly impossible to overcome. When American forces secured captured models, they extensively flight tested the airframe and mapped these exact mechanical limitations. Those fabric ailerons effectively eliminated the Zero's competitiveness in high-speed rolling engagements. Heavier U.S. fighters with rigid metallings, like the Corsair, could easily initiate high-speed rolls to evade fire and dictate the terms of combat. The A6M5 employed an asymmetric forward armament. two 7.7mm machine guns were mounted in the nose, firing at a high rate of 900 rounds per minute. Because they were positioned behind the engine firewall, a mechanical synchronization system timed the firing cadence so the bullets passed cleanly through the gaps of the spinning three-bladed propeller. This rapid nose-fire was paired with two heavy 20mm cannons mounted in the wings. While highly destructive, they fired at a slower 500 rounds per minute and were limited by 100-round drum magazines. To fire these weapons, engineers moved the trigger off the main flight stick and onto the throttle lever on the left wall of the cockpit. This ergonomic decision left the pilot's right hand completely free to maneuver the aircraft during a dogfight. Keeping this aircraft in the fight required a significant amount of combustible material. The Sakai 21 engine consumed fuel at a high rate, necessitating 150 gallons of total internal capacity. This volume was split between a 135-gallon combined capacity in the wings and a 15.8-gallon tank in the forward fuselage, directly behind the engine firewall, placing the pilot and fuel in the exact same compartment. To maintain extreme lightweight, none of these tanks were self-sealing, and none were protected by armor. A single hit from an incendiary round easily punched through the 0.5mm skin and ignited the vapors inside. That combustion turned the aircraft into an instant fireball. This immediate structural failure was the ultimate deadly consequence of the Zero's weight-saving philosophy. In low-speed environments, however, that low mass provided a distinct aerodynamic edge. The lightweight airframe, short wingspan, and hydraulically powered split flaps created a tight turning radius that heavy American aircraft simply could not physically match. The mechanical reality was so pronounced that U.S. intelligence officially directed its pilots to never attempt a low-speed dogfight with a Zero. That weight reduction also delivered a secondary operational advantage crucial for naval warfare: vast endurance. Depending on altitude and payload, the A6M5 boasted a maximum standard operational range of 1,193 miles, allowing it to execute deep strike escort missions across massive expanses of the Pacific Ocean. But as the Imperial Japanese Navy lost air superiority later in the war, military doctrines shifted drastically. The pilot's role transitioned from a conventional dogfighter to the operator of a one-way guided munition. Utilizing its immense range, kamikaze pilots approached American fleets just 30 feet above the ocean, flying low enough to evade shipborne radar. Once in visual range, the pilot would gain altitude and roll into a steep terminal dive, shouting "Banzai" as they aimed to drive a 550-pound bomb straight through an armored carrier deck. In these strikes, the Zero's greatest vulnerability became part of the weapon. The massive, unprotected fuel load was intentionally carried to maximize secondary fires, spreading destruction into the hangar spaces below the impact point. The Mitsubishi Zero A6M5 Model 52 was the ultimate expression of an engineering compromise. It was an airframe that achieved localized perfection in maneuverability and range, paid for entirely by the survivability of the pilot.